Hi everyone. Today our topic is about concurrency and we are studying background and motivation in this video. So we will look what is a process. A process or thread is a potentially active execution context. Okay, a process or thread is a potentially active execution context. So classic von Neumann model of computing has a single thread of control. Parallel programs have more than one. A process can be thought of as an abstraction of a physical process, but here only one processor will run multiple threads. Process threads can come from multiple CPUs, kernel level multiplexing of single physical machine, language or library level multiplexing of kernel level abstraction. They can run in true parallel, unpredictably interleaved, or run until blocked. Historically, this work has come from two sources: scientific computing, where parallelizing computation is important. Another is web development, which introduced the need for parallel servers and concurrent client programs. Two main classes of programming notation: synchronized access to shared memory, message passing between processes that don't share memory. Both approaches can be implemented on hardware designed for the other, though shared memory on message passing hardware tends to be slow. Principal difference is that message passing type requires active participation of two processes at either end. Okay, it requires active participation of two processes at either end, one to send and one to receive. While on a multiprocessor, reading or writing only needs one processor to control. So, there are these are the approaches. This is the principal difference between the message passing type. It requires active participation of two processors, while on a multiprocessor, it requires reading or writing only needs one processor to control. Next, we will look what is coherence. Even on a multiprocessor, there is usually local cache and a shared main memory, so issues can arise. If two processes page in a common bit of memory, they may be operating under one old or invalid data at the same time. This is known as cache coherence problem. So what is cache coherence problem? If two processes page in a common bit of memory, they may be operating under old or invalid data at the same time. So on a bus-based system, things are not too bad since processes can eavesdrop. When it needs to change its copy, it requests an exclusive copy and waits for other processor to invalidate their copies. Without the bus, this is still an open question. Race conditions. A race conditions occurs when actions in two processes are not synchronized and program behavior depends on the order in which the actions happen. Race conditions are not all bad. Sometimes any of the possible program outcomes are okay. For example, work is taking things off a task queue. So a race condition occurs when actions in two processes are not synchronized and the program behavior depends on the order in which the actions happen. Race conditions which we want to avoid. Suppose processes A and B share memory and both try to increment variable x at more or less the same time. So, very few processes support arithmetic operations on memory. So, each processor executes load x in store x. Suppose x is initialized to 0. If both processes execute these instructions simultaneously, what are the possible outcomes? Could go up by 1 or by 2. So what is next term is synchronization. Synchronization is the act of ensuring that events in different processes happen in a desired order. Synchronization can be used to eliminate race conditions. In our example, we need to synchronize the increment operations to enforce mutual exclusion on access to X. Most synchronization can be regarded as either Mutual exclusion, making sure that only one processor is executing a critical section, touching a variable, for example, at a time or else. Then condition synchronization, which means making sure that a given process does not proceed until some condition holds. Example, that variable contains a given value. One might be tempted to think of mutual exclusion as a form of condition synchronization, condition being that nobody else is in the critical section, but it isn't. Distinction is basically existential versus universal quantification. Mutual exclusion requires multiprocessor concerns. We do not in general want to over synchronize. That eliminates the parallelism which we generally want to encourage for performance. Basically, we want to eliminate bad race conditions, one that force the program to give incorrect results. Historical development of shared memory ideas. To implement synchronization, you have to have something that is atomic. That means it happens all at once as an indivisible action. In most machines, reads and writes of individual memory locations are atomic. Note that this is not trivial. Memory and buses must be designed to arbitrate and serialize concurrent access. In early machines, reads and writes of individual memory locations were all that was atomic. To simplify the implementation of mutual exclusion, hardware designers began in the late 60s to build so-called read, modify, write or fetch fee instructions into their machines. So next I will come with next video. Till then, bye.